Okay, hey guys. We're going to talk about the Michaelis-Menten equation today before we have our project group tomorrow or whenever I give this video out to you guys. So before I do that, I really just want to go briefly into rate and the rate of reaction. And so what I have here is just a generic balanced chemical equation. And so the rate of this reaction and most reactions is dependent on molar concentration, which the symbol is typically um, the the reagent, which is A in this case, surrounded by brackets. It's the concentration notation. Yeah, so it's dependent on molar concentration. It's also dependent on time. And so the rate of the appearance of a product would be equal to the disappearance of the reactant, which is why it's negative for A and B. But it's positive for the appearance of the product, which is why it's positive for C and D. And so yeah, it's just concentration over time, and then the 1 over A, that's just the 1 over the stoichiometric coefficient. Okay, so we'll really consider the rate laws for elementary reactions, which is unimolecular, bimolecular, termolecular, and so termolecular are actually pretty rare. 3 collisions happening at once doesn't happen very often, so we'll really see unimolecular and bimolecular occurring the most. And so a generic rate law is actually equal to R. It's R equal to K, which is a proportionality constant times the concentration of one reactant and the concentration of another reactant. I'm going to put A and B up here. That's just the stoichiometric coefficient. It's not really important in this case. And just to note that we want A plus B to equal 1, 2, or 3, since we don't really want to have a termolecular reaction does not happen very often, and that's just being consistent. And so now we're going to introduce the Michaelis-Menten equation. And so first we're going to introduce the enzyme substrate mechanism that happens. You write this out real quick. And so I just want to preface right here, this double-sided arrow, or this right here, does not mean that it's an equilibrium. It just means it's associating, and it's also dissociating at different rates, different constants. And another way to write this would actually be E plus S, and then it has ES, and then ES going to the product. And so I'll define these where E is actually equal to the amount of free enzyme, S is substrate, ES is enzyme plus substrate complex. The same thing for right here, and then P is the product. So that's another way to write up here. It's a little messy, I apologize. And so what the rates will be is rate 1 will be equal to K1 ES, rate 2 will be equal to K negative 1 ES, and then rate 3 will be equal to K2 ES. Okay, and so we know we have a free enzyme and we also have enzyme bound to substrate. So what is the total enzyme that we have present? It's actually going to be a sum of the two. Down real quick. It's going to be the sum of the two. And we're going to consider this mechanism, this reaction, to be at steady state. So that means that rate 1 is equal to rate 2 plus rate 3, and that's at steady state. And what does that mean? What does that mean? So steady state actually means the intermediate, oops, I forgot to write steady, sorry. So what that actually means is that the disappearance and the appearance of, my pen just bugged out a little bit. Let me fix that real quick. Sorry. So the change in enzyme substrate complex bound enzyme to the substrate is actually equal to 0. And this is actually an intermediate. It's actually intermediate. So it's equal to 0. And it's also equal, and we know that the change in enzyme substrate complex over time is actually equal to negative K2 ES plus K1 E times S minus K negative 1 ES. And what we're saying here is that the concentration of the enzyme substrate complex is essentially constant over time. It is appearing from the first rate 1. It is the product of rate 1, but it's also the reactant in rate 2. And it's also a reactant in rate 3. So it's disappearing and it's also appearing. So that's why we have negative in front of K2 times ES and K negative 1 times ES. Okay, and so we're going to pull K2 equals ES equal K2 times TS equals K1 E times S. Oops, that's a minus K negative 1 times ES. And this is actually the appearance of product. This refers to the appearance of ES. Oops, sorry, of ES. And this refers to the disappearance. Pretend I wrote that right, of ES. Or appearance of E plus S. It's the dissociation of ES into E and S. Okay, so now we'll further simplify this into ES, and we'll make E is equal to E total minus ES, so the concentration, total concentration of enzyme minus the concentration of the enzyme substrate complex times concentration of substrate minus K negative 1 times ES. And so we'll pull the ES into one side, or we'll begin to do that. So K2 plus K negative 1 times ES equals K1 times E total minus concentration of enzyme substrate complex times substrate. And then here we're going to actually define Km, which is just a combination of all the proportionality constants, just the proportionality constant of the Michaelis-Menten equation. It's also equal to substrate times total concentration of enzyme minus enzyme substrate complex divided by the concentration of enzyme substrate complex. And so we'll simplify this a little bit further. E total times S. Well, I guess not simplify, I guess we'll spread it out a little bit more. S, ES, ES. Then we can cross these out, equal to E total S divided by ES minus substrate concentration. And so we know that rate 3, what we've defined, is equal to the production of product P. It's the rate of the product being formed. Write this down. And so the velocity, the initial velocity, I should say, of reaction 3 is V0 equals K2 times enzyme substrate, concentration of enzyme substrate complex. And I want to make a note here. Velocity, in this case, is synonymous to the reaction rate. I'm just going to call it velocity in this case. So now we're going to solve for the concentration of the enzyme substrate complex. And so now we have Km is equal to E, the enzyme substrate complex, equals to concentration of total enzyme times substrate minus concentration of substrate times enzyme substrate complex. And then we have the enzymes. We're going to try and pull this onto one side. We have the concentration of enzyme substrate complex times Km plus concentration of substrate is equal to concentration of total enzyme times substrate. And then we have enzyme concentration of enzyme substrate complex is equal to the total enzyme present times substrate concentration divided by the Michaelis Menten proportionality constant plus the enzyme, the substrate complex. Yes. And so now we're going to multiply both sides by K2. And we're going to do this because I'm going to bring attention back to how the initial velocity of reaction 3 is equal to V0's K2 equals V0 equals K2 times enzyme substrate complex concentration. And so now we have K2 times enzyme substrate concentration equal to K2 times E total times S divided by Km plus S. That's equal to V0. And so it actually simplifies into V0 equal to V max times concentration of substrate over Km plus S. And why does it equal V max? Well, V max is actually equal to K2 times total concentration enzyme, which occurs when the concentration of the enzyme substrate complex is equal to the total concentration of the enzyme present, and this is due to all the enzyme being bound to the substrate. So we will have the highest rate possible of the formation of the product. So S is actually much, much larger than the concentration of enzyme. We're considering S to be much larger than the concentration of enzyme. So therefore, S is essentially constant. And that's how we find the initial rate or initial velocity of the formation of a product with an enzyme and a substrate. And I'll show you the graph real quick. I have a copy of the graph. And this is what a graph of the Michaelis-Menten equation typically looks like. So we have our initial velocity, should be V0, but it's okay. We have that as our y-axis, and it depends on substrate concentration. And so as you can see, as substrate concentration increases, there'll be a sharp incline, but as substrate tends to saturates the reaction. As enzyme concentration stays constant, it plateaus until we eventually will reach a Vmax up here. Okay, that's about it. Hopefully that made some sense. If not, ask me in person, I'll try to do better. And I'll end it here.